Why randomness is never truly random. Randomness feels chaotic, unpredictable, free from pattern. But mathematics quietly disagrees. What we call random often hides structure, order buried beneath noise, rules disguised as chance. And the closer we look, the less accidental things appear. To understand why randomness matters today, we must challenge intuition. Humans associate randomness with lack of control, with absence of cause, with events beyond explanation. But mathematics treats randomness very differently. True randomness is rare, hard to produce, harder to verify. Most systems only simulate it. They imitate unpredictability without achieving it. Early thinkers noticed this contradiction. Dice rolls felt fair. Coin flips felt impartial. Yet streaks appeared. Patterns emerged. Suspicion followed. People accused luck of bias. They blamed imbalance. They searched for hidden hands. In reality, they were sensing structure. Mathematics revealed the truth. Randomness is defined by distribution, not appearance. Patterns do not disprove randomness. They are expected within it. Clustering is natural. Streaks are normal. This realization shocked intuition. We expect randomness to alternate neatly. Heads, tails. But true randomness clumps. It repeats. It surprises. Computers expose another layer. Algorithms cannot generate true randomness. They follow rules. Outputs depend on seeds. Given the same start, results repeat perfectly. What looks random is actually deterministic. Chaos masquerading as chance. Structure wearing noise as disguise. This matters deeply. Security relies on randomness. Science depends on it. Games, simulations, predictions. Weak randomness breaks systems silently. The deeper question is unsettling. If randomness is so elusive, how much of what we call chance is actually pattern we do not yet see? Because the more mathematics studies randomness, the more it discovers rules. And those rules reveal a paradox. Randomness is not absence of order. It is order we do not recognize yet. This paradox becomes clearer when randomness is tested. Patterns emerge not because systems cheat, but because expectations are wrong. Humans expect balance. Randomness rarely provides it. Clusters form naturally. Gaps appear. Long streaks occur without cause. Probability predicts this. Emotion resists it. Mathematics formalize randomness carefully. Statistical tests replaced intuition. Distribution mattered more than sequence. A process could look patterned and still be random. This distinction changed science. Noise stopped being nuisance. It became data. Fluctuations revealed hidden dynamics. Random variation exposed structure. Physics embraced this. Thermal motion looked chaotic, yet precise laws governed averages. Randomness emerged from countless interactions, each deterministic alone. Biology followed. Mutations appeared random, but selection imposed order. Chance generated variation. Structure filtered outcomes. Randomness powered evolution. Economics struggled longer. Markets looked erratic, yet cycles repeated. Volatility clustered. Crashes followed patterns. Randomness was incomplete. This exposed limits. Some systems were stochastic. Others were chaotic. Some combined both. Randomness was not one thing. True randomness required isolation. No memory. No feedback. No hidden influence. Almost nothing qualified. Even physical randomness raised questions. Quantum events seemed irreducible. Yet interpretations disagreed. Was randomness fundamental, or evidence of missing variables? The boundary blurred. Randomness became a model, not a fact. A description of ignorance, not absence of cause. This reframing was profound. It meant unpredictability did not imply meaninglessness. It meant systems could be lawful without being predictable. The conflict deepened. If randomness hides structure, how do we tell the difference? When is unpredictability fundamental, and when is it illusion? Answering that question would reshape how risk, security, and knowledge itself were understood. And the tension was about to peak. This is where the conflict sharpens. If randomness hides structure, then unpredictability becomes suspect. Systems once blamed on chance revealed hidden feedback. Weather patterns showed sensitivity. Markets echoed collective behavior. Noise masked causality. Chaos theory made this explicit. Deterministic systems behaved unpredictably. Tiny differences exploded over time. Randomness appeared without randomness. Order produced surprise. This discovery unsettled certainty. If chaos mimics chance, how do we know when randomness is real? Prediction failed not from ignorance, but from sensitivity. Security felt this tension immediately. Weak randomness exposed encryption. Predictable seeds broke systems. Attackers exploited structure, hiding as noise. Randomness became vulnerability. Scientists responded with rigor. Entropy measured unpredictability. Tests probed memory and bias. Randomness had earned trust. Assumption was no longer enough. Even then, doubt remained. Tests detect patterns we know. Unknown structure slips through. Certainty stays unreachable. This creates a philosophical dilemma. If randomness cannot be proven, only failed at, then trust becomes provisional. We accept randomness pragmatically, not absolutely. The same applies to knowledge. Uncertainty does not mean chaos. It means incomplete information. Structure may exist beyond detection. Ignorance masquerades as chance. This realization is uncomfortable. It erodes confidence and control. It challenges the idea of pure unpredictability. It suggests limits to certainty. Yet it also empowers understanding. If randomness often hides structure, then inquiry remains valuable. Patterns can be uncovered. Models can improve. The conflict is not randomness versus order. It is perception versus reality. What feels accidental may be deeply constrained. And as this insight settles, a final question emerges. If randomness is never truly random, what does that say about freedom, choice, and control? The climax of randomness is not revelation. It is restraint. Once we accept that randomness is rarely pure, we stop treating unpredictability as absence of cause. We treat it as a signal of hidden structure or fundamental limits. This changes how systems are designed. Security assumes attack. Science assumes noise. Models assume incompleteness. Caution replaces confidence. Randomness becomes a tool, not a mystery. A way to model ignorance. A placeholder for complexity. A boundary of prediction. True randomness, if it exists, is precious. It anchors fairness. It protects security. It preserves unpredictability where needed. But most of the time, what we call random is constrained, biased, shaped by hidden rules. Recognizing this prevents illusion. It stops us from trusting noise blindly. It encourages deeper investigation. It replaces superstition with inquiry. The lesson is subtle. Unpredictable does not mean meaningless. Order does not require predictability. Freedom exists within constraint. When randomness is misunderstood, systems fail. When it is respected, systems adapt. Design improves. Risk becomes manageable. We stop asking why things happen by chance. We start asking what structure allows and what limits knowledge. Randomness did not disappear. It became contextual, bounded, useful, and perhaps that is a final insight. The universe is not chaotic. It is structured beyond our perception. Randomness marks where understanding ends, not where order fails. Sometimes the smallest shift in perspective becomes the beginning of a new future. Why